welcome back to DeepRob, to lecture 9. We'll go ahead and get started. The topic for today's lecture is going to be on training neural networks. So last time we looked at some CNN architectures and how they sort of developed over time. We'll finish off the last architecture that we ran out of time for, ResNet, in the start of today's lecture. But then we're going to start to look at how it is we can actually train the neural networks and some of the important things to keep in mind when we're doing that. Before getting into that, a couple administrative announcements, sort of reiterating. Project 2, the only thing I want to mention here is the autograder. I've just had some things on my research have come up in the past couple of days that have slowed me down from getting the autograder finished, but I am working on it. I'll try and get it up as soon as I can. I know I said in the next couple of days, the past couple of days, so it is under development, and we'll add extra submission day, we'll add extra submissions per day, so that if you're stressed about the autograder, that'll hopefully alleviate some of that. And if we need to extend the deadline because people are really stressed about it, we can do that. We'll be reasonable. But you should be able to develop still locally and use the unit testing that's built into the notebook cells. So that's project 2. The only other administrative update is on the final project paper selection survey. Just a reminder, it's due tomorrow night at midnight. It's on Gradescope. You should be able to access it and just fill out what areas are most interesting to you. If there's a specific paper that you most want to present, then let us know there, or a team that you want to work with for the final project. So this survey is just for picking out the papers that you'll do for the review and the presentation. For the technical implementation and the reproduction, you can do a different paper. So this is just for the first 2 deliverables of the final project. All right, before getting into the lecture content, any administrative questions I can answer? Okay, so where we left off last time was we were just getting up to the ResNet architecture. So we had seen how in this ImageNet competition, starting with AlexNet and then onward, these deep neural networks and these neural networks of increasing depth were winning the competitions and had sort of a trend in how they were designing the architectures. They started using sort of fixed design principles. They were incorporating max pooling while also doubling the channel dimensions. And that then got us up to ResNet, which then had this huge order of magnitude increase in the depth of the CNN that was used. And so interestingly though, with ResNet, it wasn't just a matter of they found a way to increase the depth from let's say having access to additional compute, and then it just magically worked. It was actually a little bit more complex than that. So what happened with ResNet was they had batch normalization. So we were seeing networks that were being trained with those 20 layers, 10 plus layers of depth. And so ResNet at first sort of thought, okay, let's increase that further. Let's try training a network that has on the order of 100 layers. And what they actually found was that initially, the model that had those additional layers actually had a higher test error than models with fewer errors. So even controlling for as many of those other variables as they could. So the same data, the same training regime, a lot of the same hyperparameters within the layers that they were choosing in terms of the stride and the padding and the kernel size. But yet this deeper layer, which should have been able to fit more complex functions, was having a higher test error. And so their initial kind of guess, or their initial hypothesis, was that the deep model must be sort of overfitting somehow. It must be sort of overfitting to the training set, so that then when we go and apply it on the test set, it's performing worse. And the reason why it might be overfitting is because it has all these extra parameters. It has all this extra flexibility that it could learn these overfit to these more complex patterns in the data set that the smaller model couldn't. But what they then sort of found was that actually the model seems to be underfitting, because even on the training error, so even on the data that the model is being trained on, this larger model had a larger error than the smaller model, which is really kind of counterintuitive, right? Because the fact that it's underfitting somehow is counterintuitive, because it has all these extra parameters. It should be able to fit to at least the same test error as the smaller model was fitting to. And so then the question was, okay, well, how can we try and correct for this? Or what might kind of be causing this underfitting performance of these larger models? And so the hypothesis that the authors proposed in the paper is that this is actually an issue of optimization. So we have these bigger models now that, even with batch normalization, are actually not well suited for the stochastic gradient descent that we're using to train the models. And so they're just sort of harder to optimize, these larger models. So the goal then with ResNet, what they set out to try and to try and construct as a way to test this hypothesis was, could we try to change this deep network so that it could at least learn the same thing, or like try and ensure that it could learn the exact same thing as the smaller network. And maybe if it could learn the exact same functions that the smaller network can, then we would somehow be testing whether or not like this challenge of optimization is in fact the case. So the actual architecture that they propose to ensure that these deeper networks can model the exact same functions that the smaller networks can model is by adding these residual connections, which is where the name ResNet comes from, where what they'll do is, so in the standard kind of feed-forward convolutions that we've been looking at, what you might call a plain block is you'd have some input tensor X come into a convolutional layer, pass it through a nonlinear ReLU layer, and then pass it through a second convolution layer. And you could sort of chain these blocks together. So that's what we saw with VGGNet and AlexNet and GoogleNet. What ResNet then proposes is, okay, because we want to allow, let's say, this block to model an identity function so that we can still ensure that this larger model could potentially learn the exact same function that the smaller models can, what we're going to do is carry forward our original input tensor here, X, as then like with an additive operation at the output of this residual block. So what we'll do is we'll take X, we're going to pass it through a convolution, pass it through that nonlinear ReLU, pass it through a second convolution, and then that output that we get, that output tensor from these two convolutions gets added back together with our original input tensor. And so you can imagine that if these convolutions were set to be all zeros in the kernels, then this actually will be exactly the identity transformation, because these convolution layers will all of a sudden be doing nothing to transform the input. They'll just be carrying forward the data. And so then this is a way that you could ensure, if you had these residual blocks built into your network, that at every layer, it's as if the model wanted to learn to not use the layer, it could learn to not use the layer. So it could sort of like learn to not use this added complexity that we're maybe giving it with extra depth. And so hopefully this will make the training then easier. That's the thinking behind ResNet. And so it's a really, I will point out, like going back and reading ResNet, I mean, all these papers is a great exercise, but ResNet's very nice in that they go through this logic and how they had those initial results and then these hypotheses that they wanted to try and correct. Okay, so given this residual block structure then, what ResNet ultimately is going to be is chaining together these residual blocks in a similar design approach that was used, for example, in VGG. So the idea is, just like VGG, we're going to say that each residual block will be constrained to be like a 3x3 2D convolution, and then what we're going to do is kind of also similar. We're going to say that the first block within each stage, so the overall network is built into these stages of residual blocks, based on like the color in this diagram. So within each stage, the first convolution layer is going to have the spatial resolution and double the number of channels. So it's of similar kind of architectural principles that were used in VGG. Similar to GoogleNet, ResNet uses a very aggressive stem at the input of the network to try and decrease the spatial resolution pretty rapidly. So these parameters, I think these are all the exact same parameters as we saw with GoogleNet for the input stem. And then also similar to GoogleNet, the output stem, like kind of final classification head on ResNet, uses global average pooling instead of max pooling. So you can see there are like these similarities from these earlier architectures that we looked at to ResNet, which makes sense because there were only kind of a couple years between ResNet and VGGNet and GoogleNet. So within this paper, ResNet is not just a single architecture. What they do is they propose variants of different depths. And so that's similar to how, for example, like the VGG paper and also the GoogleNet paper. It's pretty common. It's a pretty common trend where when you propose a network architecture, you might have like a variable number of layers within your architecture. So you could have like a small version, a medium version, a large version, or like in VGGNet, there were 5 versions. In ResNet, I think there's even more. So ResNet 18 has, you can see here, like it has these 4 stages where within each stage, they control how many residual blocks are used. So that's then adds up to like the overall depth of the network. ResNet 34 is a larger version of ResNet. So you're using the same residual blocks, but just you have more of them throughout these stages. And so what they ended up finding was that having these residual blocks does allow the model to ultimately beat the state of the art on image classification. So it does sort of solve that challenge of optimizing these increasingly deep networks. So for example, like ResNet 34 ended up with a top 5 error of 8.58, which was beating out then VGG. So by having these just by changing the network to be these residual connections, ResNet 34 was able to sort of fix that optimization problem. Because in their original design, they were trying the same architecture as ResNet 34, just without the residual connections. And that was the model that had that higher test error and higher train error. So that's it's a very cool result. And also pointing out, like, this model actually had even higher computational efficiency than VGG. Mostly, I think it's because the VGG, you'll remember, had the like some pretty heavy fully connected layers at the very end, whereas ResNet has, because they use like the global average pooling and kind of similar to GoogleNet, they can reduce a lot of that compute towards the end. This part I'll kind of go through a little bit fast. So one other interesting part of ResNet, as in a few of their proposed architectures of like increasing depth, they propose using these bottleneck layers where, so what they'll do is they'll add a 1-by-1 convolution at the start and the end of a block in order to reduce the channel dimensions down before applying a 2D convolution. So the thinking is 2D convolutions are really compute intensive. So what we could maybe do with a 1-by-1 convolution is just like drastically reduce down the channel dimensions, maybe let's say by a factor of 4, and then perform the compute expensive 2D conv on that fewer channel dimensions, but same spatial resolution, and then use one more 2D conv to kind of upsample the channels back to the original number so that our final like residual connection, this add like element-wise addition, can actually be performed. Yeah, so the residual blocks then are used, or these bottleneck blocks are used in, I think it's 3 of the overall architectures that they propose. So in the ResNet paper, the original one, they proposed like ResNet 18, ResNet 34, ResNet 50, 101, and 152. All of these, so then here, this table just gives like some of the hyperparameter settings for the different stages. I'll point out though that all of these architectures are still very heavily used in current models. So typically what you'll see done is you'll take maybe a pre-trained, let's say ResNet 18 on ImageNet, and then you'll fine-tune that network as part of your proposed architecture for pose estimation or for maybe like underwater like object detection. So even though like maybe underwater objects are not well represented in ImageNet, a lot of the features that these ResNet models are learning on ImageNet can actually transfer over to other tasks that we're interested in. So it's very common that you'll actually be working with these models in practice. And then which specific model you use will sort of depend on how much compute you have available. So if you have less compute, you'll use a smaller model. And also depending on the size of your data set. So if you have like a larger data set, then you'll potentially want to use like one of the larger models, which can, because you have more data, you can avoid some of the overfitting. Whereas if you have less data, then I would suggest starting with the smaller model so that you can avoid the overfitting with fewer parameters. Okay, so that's ResNet. So this architecture was proposed, and it actually swept all the, like, there's sort of sub-competitions by this point within ImageNet. So it won first place in all of them. And since then, like this idea of like residual skip connections are used very widely within architecture design. So looking now at this set of models that we've kind of been talking about, on this plot here, what we're showing is the top 1 accuracy on image classification for different neural network models. This is on the left-hand side. We have only talked about a subset of these. The more recent, like these inception models, are kind of a combination of ResNet plus inception. So we didn't talk about those, but if you're interested in the paper, you can find that online. So that's one way to compare models, right? Is just to look at how well do they perform on some benchmark task, in this case, image classification. Another way that we could compare models is based on how many parameters are they using, what's their memory footprint, how much compute, and then also what's their accuracy. So on this plot, what we're showing is on the vertical axis, it's the top 1 accuracy on image classification, and then on the x-axis, it's the number of floating point operations that the model requires for a forward pass. And then the actual area within these circles is the number of parameters, if I'm remembering correctly. I think it's the number of parameters that the model has. So VGG has like this, or actually I take it back. It's the amount of memory footprint that the model has, which is to some extent related to the parameters. So VGG has like this really, really big memory footprint because it had a lot of those large fully connected layers, which were taking up like a lot of memory at the end of the architecture, but it achieves pretty good accuracy. In contrast, then GoogleNet has this way smaller memory footprint, because remember, the goal for GoogleNet was to try and maybe deploy it on like mobile devices where you don't have like a lot of memory and a lot of compute available. It's also very compute efficient. So you can see on the x-axis, it's like less than 5 gigaops. And then in contrast, like AlexNet, that original paper is pretty efficient, probably because it was constrained so heavily by the GPU resources available at the time, but it has lower accuracy and a kind of medium-sized memory footprint. And then up here, the ResNets are like the more recent architectures, which are kind of like the most accurate, but then like a middle ground between compute. Okay, so that's kind of a quick pass through ResNet, and that then brings us up to what we were sort of supposed to cover at the end of last lecture. So we looked at between AlexNet, moving to VGG, then GoogleNet, and ultimately ResNet as this trend in CNN architectures for image classification. So given this, though, just setting up a CNN architecture is not enough to, let's say, win ImageNet. You also then have to train these architectures. And so we saw to some extent how designing your actual structure of the architecture can be used based on the results you see from training, but that's not everything, right? So there's going to be a set of other topics that we have to look at to understand how we can actually train these networks to achieve the accuracy numbers that we saw. So in today's lecture, what we're going to be talking about is sort of like the setup that goes into training. So after you've defined your overall architecture structure, you still have to choose like the activation functions that you use as one hyperparameter, how you preprocess the data, how you initialize the weights within all of these layers, how you regularize those weights. So all of these hyperparameters are going to very much affect what the ultimate like performance characteristics in terms of accuracy are for your final model. And then next lecture, what we'll talk about is some additional concepts within training CNN architectures that we have to be aware of. So like learning rate schedules. So it's actually the case that typically what you'll want to do with stochastic gradient descent is change the learning rate dynamically based on how the dynamics of training have gone up to the current point within training. Also then looking at like some techniques for how we can actually perform hyperparameter optimization, and then also like ensembling models, which is where you average the predictions of multiple models to produce a better prediction than your original individual models, and transfer learning. Okay, so to start out with today, the first topic we'll talk about within this kind of context of training our neural networks is going to be the choice of activation functions that we use. So you'll recall that activation functions, they take the output from some layer and they're going to pass it through generally a nonlinear function to then produce some output activation. And to some extent, this concept is inspired by biology. So we haven't gone into too much depth on this because I don't have a biology background, so it's really not an area that I'm comfortable talking about. But historically, there has been biological inspiration for these artificial neural networks. Principally, the kind of core idea is that a high activation in an artificial neural network, to some extent, is modeling the actual like chemical activation that occurs within a biological neuron. So like within a biological neuron, when you have like this synapse that maybe has like, or you have a neuron that has multiple synapses coming into it from other neurons, if all those incoming synapses are firing and producing some chemical like activation at this cell body here, which is representing like an actual neuron, then that cell body, that individual neuron then is going to decide whether it should fire, maybe based on like a nonlinear activation, like a nonlinear activation function locally. So there is some biological inspiration to what these artificial activation functions are modeling, but from my standpoint as a roboticist, I think I'm not a biologist, so I kind of stay a little bit at a distance from some of those comparisons. But if you're interested in that, there is a lot of literature that tries to model biological neurons with artificial neurons. Okay, but for our purposes, on the robotic side and applying these, so there's a set of activation functions that are nonlinear activation functions, which we talked about in the neural network lecture. So you recall that we talked about the sigmoid activation function, so the one up here which squashes input values to be scaled between 0 and +1. Hyperbolic tangent, which is a scaled and shifted version of sigmoid, which squashes the input values to be between -1 and +1. ReLU, which we mentioned is the most common activation function for our neural networks, which is going to be like a constant 0 output for any negative values of input, and then it's just a linear function for any positive values that it has as input. And then there are these other ones which in the past we kind of skipped over and we said we would talk about in the future. So today we'll talk a bit more about these other activation functions. But to start with, let's think about the sigmoid activation function, which was one of the activation functions most heavily used early on within some of the initial neural network development. So you'll recall the key property of this function is that it squashes the input values to be within a range of 0 and +1. So if you give input to the sigmoid function of exactly 0, you'll get output that's exactly 0.5. And then as you increase, like towards infinity, sigmoid will converge towards +1. As you increase the input towards negative infinity on the left, sigmoid will converge towards an output of 0. And so there's two reasons that are sort of cited or pointed to as why sigmoid was popular for an activation function early on. One was because you could interpret sigmoid as like this kind of saturation behavior that sigmoid has, right? So like this more positive, the input you give it, like the output saturates towards 1, and the more negative it saturates towards 0, is to some extent inspired by that idea of a biological neuron firing based on how active its inputs are. So that there's one interpretation there. The other interpretation is that because we're squashing the input values to be between 0 and 1, if I pass my network output through a sigmoid, I can now treat it like it's a probability because probability values have to be between 0 and 1. Now, I like probability theory, and I think to some extent that's an abuse of probability theory terminology, but it's true that sigmoid does squash its output values to be between 0 and 1. So you could potentially interpret the output of a sigmoid as a probability. Having said that, so sigmoid was very popular early on as an activation function within neural networks, but there's 3 core problems that have been found for using it. So it was chosen at the start kind of maybe based on some of these interpretations, but then in practice we found that there were actually like issues with it that some of the other activation functions which kind of came into use later on solved. So we'll look at what the problems were and how the other activation functions solved them. So the first problem with sigmoid, and this is really the main problem, is that if we have neurons within one of our network that become saturated, that saturation is inherently going to kill, we'll say, the gradients during training. So what we mean by that is, by saturation, what we mean is if we have some neuron which at the start of training has a very, very positive value, it's going to correspondingly have some activation in this region, right, like close to +1. And if we think about what the gradient is going to be for sigmoid in that region, just imagine what the slope is. It's going to be a line that's roughly pointing along the horizontal axis, so a slope of 0. So if we think about what that would do, right, so when sigmoid has input that's very positive, or very negative, like -10, or very positive, like +10, the actual local gradient, so like the d of sigma with respect to the input, so d sigma dx is going to be approaching 0. And so because of that, when we apply backpropagation, the overall update that we get for one of our weights, which might have been producing the input to a sigmoid, is going to correspondingly have an update that's very close to 0. And so this can make training very, very slow, and actually, like, the slower, the more saturated the specific neuron is. So this is one issue, is it slows down training. Let me kind of pause and see if everyone is following so far on this idea of like a saturated neuron and how the gradient for inputs that are saturated will be close to 0. Okay. So another way to kind of interpret that is there might be a lot of information during training coming from our upstream gradient. Like there might actually be like a good training signal that says how the output of the sigmoid should change. But just by the mere fact that on this specific training example, maybe the sigmoid had an activation that was very high, that training signal then is not going to get propagated backward beyond that one layer. So all the preceding layers don't benefit essentially during training. Now that's kind of hypothetical on the fact that we have neurons which are saturated, but it turns out in practice that we often see neurons that become saturated. So that's the first issue. The second issue is that sigmoid outputs are not zero-centered, right? And that is, again, that's kind of just inherent in how this function is defined, because all of the outputs from sigmoid are always going to be positive. They're always going to be either slightly above 0 or up to just below 1. But you're never going to have output from the sigmoid which has a negative value. So let's think about why that could be a potential issue. So the first thing to think about is, let's put this in the context of just a feed-forward linear layer. So this equation here is showing like let's say the output, so some hidden layer, output from one of our fully connected layers as the result of a summation over, let's say, j input dimensions between our weight matrix for a specific class I and the output from some sigmoid over the input hidden channel for this jth dimension from the input hidden layer. So that's maybe said like a little bit more clearly here. So H sub I upper L is the ith element of the hidden layer at layer L within our overall network before activation. We pass that through the activation. And then W and B are the learned weight matrix and bias matrix for our linear layer. So given this setup for just a linear layer like we've been talking about, let's think about what happens on the gradients for this weight matrix. So we can write that out using our kind of notation from backpropagation. So what we want to calculate here is the derivative of the loss with respect to an individual element within our weight matrix, and then this overall will form our gradient matrix for dl dw. So using our notation, we know that that's if we take the local gradient for our particular output here with respect to the weights at this layer multiplied by our upstream gradient, which is the derivative of the loss with respect to this output hidden layer. And we can then substitute in, based on our knowledge of how the hidden layer is essentially like that matrix multiply, what this actual local gradient is going to be in the case of a linear layer, right? So what we know is, because the matrix multiplication was what we call like that swap multiply operation during backprop, we know that the gradient for the weights is just going to be the actual kind of other term in the matrix multiply, which here is the output from our sigmoid operating on the input to this layer, multiplied then by the upstream gradient. And so the issue then to think about is that if sigmoid is ensuring that all of the output from this term here are always positive, always have a positive sign, that's going to necessarily mean that every single row of our gradient matrix has the same sign. And they're all going to have the same sign as the upstream gradient. So why is that potentially an issue? Well, what that means is that when we go and try and use that gradient matrix for gradient descent, because every row of the matrix has the same sign, it's constraining what dimensions in parameter space gradient descent can actually move within. So in this figure, this is an illustration of that concept. So the two axes are representing two dimensions within parameter space. So this might be like W1 might be the x and W2 might be the y-axis. And it might be the case that if the optimal direction, if we initialize our weight matrix, let's say at 0, the optimal direction for stochastic gradient descent might point somewhere that's not along one of the axes of the parameter space, but using sigmoid is going to constrain our actual gradient updates during gradient descent to fall along these axes, where we're either always moving both parameters in the negative direction or both parameters in the positive direction, just by a mere fact of using sigmoid at all. And so what that can lead to is slower convergence times, but also just this kind of like, this inefficient optimization during gradient descent. In practice, this is kind of a conceptual issue. In practice, you can actually still train with sigmoid on some problems and get decent performance, which maybe calls into and actually get convergence, which calls into question maybe this argument. Potentially why we don't see this come up in practice is because we're training on mini batches. And so when you add in a mini batch to the gradient calculation, you could potentially start moving along these along these directions within parameter space that aren't constrained to the axes of parameter space. So that's one issue why. And also batch norm can potentially help alleviate some of this. So this problem is like hypothetical, but in practice, it might not be the main reason why sigmoid is an issue. It's more so that you'll find that the gradients go towards 0 when you use sigmoid. And so the convergence slows down for that reason. A third reason why sigmoid has an issue is that it uses this exp function. And so that actually has a computational expense associated with it that, for example, the ReLU doesn't. The reason behind that is exp is what's called the transcendental function, which means to actually compute it in hardware, you have to have some form of a loop or a recursive operation. Whereas with a ReLU or with a non-transcendental function, you can calculate them with a discrete fixed number of like algebraic floating point operations. So that's another kind of downside. But again, that's like a smaller one. Exp is like a little bit expensive, so maybe we would want to find something like a little bit better. Again, in practice, this like don't take number 3 don't put too much weight on this third issue, because in practice, when you're working with like a GPU device, when you actually transfer memory to and from the CPU to the GPU, that memory transfer is actually way more expensive than the compute on the GPU device. So again, the second and the third are more kind of conceptual issues, but in practice, they're not so bad. The main issue is number 1. You will see this in practice. The gradients for saturated neurons will be nearly 0, and your training will slow down and even stop effectively with sigmoid. Okay, so that's kind of the characteristics of sigmoid. The next activation function we want to look at is hyperbolic tangent. So we mentioned this is a shifted and scaled version of sigmoid. So in particular, what we're doing here is we're sort of shifting the sigmoid curve sort of down. So now it does extend into like the negative values of output, and then we're scaling it so that it still has output scaled between -1 and +1 in this case. But it still has this issue that the gradients will be saturated when you have like very, very positive input values, right? Like in this range, or very, very positive or very, very negative input values in this like negative range. So it potentially fixes that second issue that we had with sigmoid, because now we have zero-centered output from this neuron, but it's still going to have the gradient saturation issue. So we still have that. So that brings us then to ReLU, which actually fixes these two issues. So in ReLU, we're not going to saturate, at least in the positive region, because it's just a linear function. So as long as our neurons stay in that positive region, at least, we're always going to have gradients that are going to be greater than 0. In the negative region, there is the issue that the gradients will be exactly 0, in fact. So in some sense, in the negative region, it's potentially even worse than sigmoid, where in sigmoid, the gradients would be slightly above 0, so there's maybe be some chance with enough steps you could escape the saturation. With ReLU, though, they're going to be exactly 0, so you'll have like neurons kind of die. But even with that potential issue, so ReLU is very computational expensive. It's just that max operation. And in practice, it converges very, very fast. So I think we mentioned this in the past. ReLU is generally the most common activation function you'll see in practice. So for this overall discussion of activation functions, it's kind of important to think about how these other activation functions can play some role and what the historical use for them was, but don't put too much, don't be too concerned about which choice of activation function. A general rule is start with ReLU, and then if ReLU doesn't work, there might be something more serious wrong with your architecture or your training setup. And then you move towards those other activation functions for more niche use cases. So like in transformer architectures, there's some niche activation functions, or like in image styling, sometimes you'll have some niche. Or NERFs actually have a niche activation function, but we'll maybe talk about that later in the semester. Okay, let me pause, get a drink. Yeah, question. So the question was, why does ReLU converge faster than sigmoid and tanh in practice? So I would say to some extent, it's that property of, in sigmoid and tanh, the gradients for saturated neurons are close to 0. I can't explain why it is that for ReLU, you don't find many of the neurons within your overall network kind of dying off. I don't know why that doesn't happen, but because not many neurons die off, all those neurons that stay alive have gradients that are much, much bigger than you would have in sigmoid or tanh because of this linear portion of ReLU. Yeah, good point. That's true. So yes, so ReLU is not zero-centered output, and also the gradient is exactly 0 when the input value is less than 0. So let me think. I'm trying to think if that's coming up. That's true. I think so. One thing is batch normalization can to some extent alleviate the issue of not having zero-centered output, right? Because if you follow like ReLU up with batch norm, that will then ensure that your data is zero-centered. So I think that is the fix. But you're right, ReLU by itself does not have zero-centered output. So just using ReLU without batch norm can result in issues. Yeah. Okay. Okay. So thinking about what happens in the case of backpropagation with ReLU activation. So in the case of very negative examples, or very negative input or input that's exactly at 0, our gradients here are going to be exactly 0. So even if we have upstream information, that's going to actually get destroyed because this product with a zero term is going to be 0 for the downstream gradients. In the cases where we have positive input to our ReLU function, the gradients then are just going to be essentially linear. So we'll retain information during training. So on this topic of like what I was referring to as dead neurons, one thing that can happen with ReLU is if you imagine, so this plot is it's hard to imagine this for image data sets, but if you imagine that this figure here, this data cloud represents like our full training set, and this portion in this like lower right hand quadrant represents our like activation through a ReLU neuron for all of the examples in our training set being 0. If that's ever the case, then that neuron effectively is completely useless within our overall network. Like we're still performing compute for the forward pass and the backward pass, but because it doesn't activate on any of the training examples, it's never contributing to the actual like decision. It's just 0. It's always producing 0 contribution. And so once a neuron within your network falls into this case where all the training examples produce 0 activation, it will never have a chance to escape because consequently all of the backprop through this neuron will also not contribute towards changing it. So that's something to be aware of with ReLU. So the question was, if you use batch norm and you're normalizing your input data to be between 0 and 1? That's true. Yes, that's true. Well, if you apply batch norm, the output of batch norm will not be between 0 and 1. It will be 0-centered. Like it will ensure that it's 0-centered. So it could be between negative some value and positive some value, depending on what the input distribution was. So for that 0 centering. Yeah, you are. So yes, so the question was, so with ReLU, because you're performing like this max, if the input to a ReLU neuron has negative values, like let's say you passed batch norm and then ReLU, so you have values that are negative and positive insured coming in, then aren't you losing information from all those negative values because they're going to be squished to 0 through ReLU? And that is the case. So ReLU does destroy that information about like how negative was the information, or just how negative were the activations that were coming in. That's gone at this point. So like the downstream neurons can't use the fact that the input to this neuron was maybe very negative or mildly negative to inform its decision. It only knows that they were less than or equal to 0. Would that property of ReLU affect the loss during training? It would affect the loss just as the nature of ReLU affects your ultimate like decision, like the output of your network, and that output of your network is what's what's controlling your loss. So a slight variation to ReLU then is what's called leaky ReLU. And so the idea here is to try and ensure that our ReLU neurons never go through that dying. So they always have some gradient, even in the case of negative input. So what they'll do is they'll define, it's essentially a piecewise linear function where for input values that are greater than 0, it's just a linear, it's just like a linear function, so it's just x. But then for values of input that are less than 0, it's actually some scaled linear function where the scale parameter here, a, is a hyperparameter. So you can actually tune what you want the slope of that portion of the piecewise function to be. And so the benefit here is it still has properties in practice that similar to ReLU, so it'll converge a lot faster than sigmoid and tanh. It has a benefit over ReLU in that, like we were saying, these neurons won't die because you're never going to have a portion of the space here where the gradient is exactly 0. And yeah, so it does have benefits. I would say ReLU I still see a lot more in practice. So I would say look to the paper cited here for maybe if you're curious about what some of the downsides might be with leaky ReLU. Another version of this is what's called parametric ReLU or PReLU, where you actually try to learn this slope dynamically. So you treat that A term within the max as something that you would backprop into. So it's not just hyperparameter, but it's actually learned. So moving on then, another variant of ReLU is called ELU, so the exponential linear unit. So once again, it has the benefits of ReLU, where it does converge a lot faster than sigmoid and tanh. It has let me see. So what's different from leaky ReLU? This adds some robustness to noise, but I think the reasoning on that is somewhat debatable. The main takeaway is that it's another variation of ReLU, where in this case you can actually have some negative values produced as output. But beyond that, so one downside is that it requires this somewhat expensive compute of the X function. One more that we'll talk about is scale exponential linear unit, so CELU. This one is interesting in that the authors who proposed this as an activation function showed that you can actually, using this activation function in some contexts can actually avoid the need to use batch norm, and that if you have very specific chosen hyperparameters, as you can see that are shown here, to go along with this function, this is actually equivalent to using this function is equivalent to using ReLU with batch norm. So this has maybe the benefit of being slightly more computationally efficient than using ReLU plus batch norm because you kind of bake them in together. Having said that, it's we're not going to go into the details of how it is that that's the case. So you can go to the original paper if you're interested. They go through the full derivation of how that of how that's the case and what assumptions go into that. But it's beyond the scope of today's course. So another one then, and this one I would say you will see increasingly, but it's mostly in the transformer architectures, is a Gaussian error linear unit, where it's once again it's very similar to ReLU, but the idea here is that you're adding you're adding randomness for one thing. So what you'll do is you'll say that based on how large the input to my layer is, I'm going to sort of stochastically control kind of how similar to ReLU I want my output to be. So what you do is you would sample a random value from just a Gaussian distribution that's zero-centered and unit variance. And then you'll scale your input by the probability that this random sample you have is less than the input. So what that effectively does is for values of your input, which is the lowercase x, which are very, very large, the probability that this Gaussian sample, which is the random variable capital X, are less than this very large input lowercase x is very high. So in all likelihood there, what you would expect is to have linear output, right? This probability term will be close to 1, and so your output is just going to essentially be like a linear function from similar to ReLU. In cases where your input is very small, in cases where this x is small, it's relatively unlikely that this random sample you have is going to be smaller than your input x. And so in that case, then in that case, then what you have is like this. It turns out to be this performance that's shown here. So again, like I'm not going to go into like the derivation of how this was used. One slight thing to kind of note is that it's somewhat closer to ReLU than this preceding function, or in a couple of the preceding ones, which would always produce negative output for negative values of input. This function will approach 0 for extreme negative inputs, but it does still have this region of negative output close to 0. And so one thing that's kind of interesting that can do is, so the other point is that this is not a monotonically increasing function, whereas all of the preceding functions we looked at were monotonically increasing. So what you can have is, for example, the value of output produced by an input from where my cursor is here is the exact same value produced by the input where my cursor is here. And so to some extent, similar to like this question about how downstream neurons will interpret, with ReLU, downstream neurons can only interpret a value of 0 to mean that the input to that neuron was some amount of negative, but not know how negative. There's a similar kind of process happening here, except in this case, if a downstream neuron sees a specific output value that's negative, it again has this kind of like, there's some uncertainty baked in to just how negative was the input to that neuron. So in some sense, it's like a regularizer on downstream neurons because they can't kind of overfit to like just how negative was the input to this network, or to this neuron. So it's very common in transformer architectures. So I think later in the semester we'll talk about transformer architectures. In classification architectures, you see it less, and it's a more recent activation function. Having said all of that, I think it is to some extent interesting, probably more on the theoretical side, to look into like these activation functions and really try and understand why does one choice of activation function affect my downstream performance. But at a broad level, don't overfixate on it. It is a hyperparameter, and it turns out that usually, if everything else in your network is sort of set up correctly, the specific choice of activation function will have a very small effect on your overall performance. So these results here come from this ICLR workshop study, which looked at controlling for a network architecture and looking at like what was image classification performance if I just changed the activation function. And so what you'll see is that even like the most extreme drops that they found was like going from like 93% accuracy to maybe like 94.7. So you're talking like 1.5% accuracy change. So it is a hyperparameter. It will affect performance, but it's generally speaking, it's not going to make or break your performance. So that's like want to caveat that. Generally speaking, stick with ReLU to start, and then you can maybe go to like leaky ReLU if you want to sort of like try and do a parameter search to marginally increase your performance. So yeah, don't worry too much about these activation functions. Generally speaking, stick with ReLU. Yeah, some recent architectures are starting to use this GLU instead of ReLU, but again, it's kind of like a final optimization for performance. Okay, before we start talking about data preprocessing, can I answer any more questions about the activation functions that we've looked at? So the question was, once a neuron gets saturated, is there any chance for it to come back to normal? So it depends on the activation function. So for example, like in the case of sigmoid, if you have a saturated neuron, that essentially just means that the gradient there is going to be close to 0, but it's not going to be exactly 0. So like with sigmoid, in theory, with enough steps, you could recover like a non-saturated neuron. I would also point out that with your sampling of mini batches, that also is going to kind of make more complex the analysis about when neurons become saturated, because it might be saturated from one mini batch, but then on the next mini batch, it's not saturated. So if it's saturated on the entire data set, though, then like I was saying, for sigmoid, there will be some gradient that's close to 0, but not exactly 0. So in theory, with enough steps, you could escape it. With ReLU, for example, if ReLU has an output activation of 0 for every single image in your training set, that will never escape, because the parameter updates are not going to be changing that. Like, we're not going to change that activation output. So the question was, if a ReLU neuron's output activation is 0, or yeah, is 0, how will the network try to escape that? To some extent, I would say it won't try to escape that. The only thing I suppose that could happen is it might be the case that if you have multiple neurons in your network, which you will in practice, then the gradients that are flowing through some of the other neurons will affect the weights, which affect the activation seen as input by this neuron. So you could get there could be some feedback there. But beyond that, though, there would be nothing. So if you have a neuron that is kind of isolated, like its inputs are not affected by weights that other neurons are feeding into, then it will never escape the saturation. That would be it's a drawback. Like the saturation is a drawback of these activation functions. Yes, right. It's extremely unlikely that all of your neurons are going to fall into that for all training images. So that's like the big caveat with this discussion is that if you're using mini batches with gradient descent and you have an architecture that has thousands or millions of neurons, there's a lot of feedback happening between, like when you do backprop. So don't worry too much about the neurons dying. It's not really an issue in practice with these very large networks and if you use ReLU. With sigmoid, it still does come up, but with ReLU, it does not. And I would say, generally speaking, that's the only time you will really ever see sigmoid used now, is for that. Yeah, so the question online was, we were saying like don't ever use sigmoid, but what if for like you want your output of your network, just at the very end, to be scaled between 0 and 1, then yes, that's where you will still see sigmoid used, is if you want a final output score that's between 0 and 1. Yep, question? Yeah, so the question for those online was, why not just use leaky ReLU if it fixes the issue with ReLU saturating for 0 output activation, and it's more efficient than these other like ELU, CLU, GLU. You will see leaky ReLU in practice. I would say ReLU doesn't, like this saturation can happen, but it doesn't happen in practice enough for it to really be a true in practice downfall of ReLU. So you'll see leaky ReLU used, but I still would say you'll see ReLU used even more, despite the fact that in theory ReLU could have this saturation at 0 that during backprop is potentially bad. Yeah. Kind of similar to batch norm, these activation functions, and to be honest, it's still like training of neural networks in general. There's not concrete theory to understand, because these optimization problems are so hard and there's so many hyperparameters and they're non-convex, there's not solid theory to like that anyone has right now to say like, this is exactly why leaky ReLU will be better than ReLU in these specific data sets and not those. It's an interesting topic, but it's more theory side than like robot side. Okay. So the question was, if we do want a network that will output values we could interpret as probabilities, why would we not just define a loss function why not avoid using sigmoid but define a loss function that can be used for probabilities, right? So you're thinking of like, a loss function between 0 and 1? Well, the loss function, right, is dependent on having a label to go along with your data. So at test time, the loss function is not used. So at test time, if you want your model to predict a probability, if you were going to use the loss function to generate the final probability, you would need maybe a label as input to the loss function. Having said that, though, in practice for numerical stability, there are variants of loss functions which will basically take the raw scores of output from a layer and use those during training as opposed to a sigmoid. So you wouldn't actually run your final output through a sigmoid before passing it to the loss. The sigmoid gets baked into the loss calculation, And then at test time, you would just take whichever, let's say, score at the final layer had the max raw score and use that as your prediction. So that way you could avoid even, it gives you some numerical stability, but so that's kind of in that, along those lines, but slightly different. Okay, great, cool questions. Okay, so activation functions, yeah, so just the broad summary, stick with ReLU to start, maybe leaky ReLU, and otherwise it's an interesting theoretical question. So now another consideration that we should have for training is how it is we pre-process our data for actual training. And so we have talked within batch normalization about this idea of pre-processing, and in particular what we were talking about with batch normalization was zero centering the data, and then also scaling the data to ensure that our neurons had unit variance. And so graphically, that concept is depicted here. So if you have some data set that has a mean which is offset from the origin, so in this case, the mean of this original data is somewhere where my cursor is kind of highlighting. And also it has a variance which in the 2 dimensions is not unit variance. So in this, along this this dimension where my cursor is here, it has a very large variance, and also along this dimension, the y dimension, it also has a very large variance. So shifting the data will zero center it, so you can shift it by the original mean to now center the data at the origin. And then if we scale the data based on the standard deviation, just like we talked about in batch normalization, you can ensure that the data set has unit variance. So in this case, this is kind of like a 2D example. This is what batch normalization is doing in the case of our tensors, but this is actually a useful technique to use not just for hidden layer activations within a neural network, but actually for the original input. So typically what you'll see done with images is you will actually shift the input pixels based on the color distribution in your training set, and you also so you'll have zero mean in the color channels and also unit variance in the color channels. Less often used would be like more complex forms of normalization where you might apply like whitening of the data, so you ensure that you actually have unit covariance, so not just variance along the individual axes of your data space, but the actual covariances, right? Because in this previous slide, we're not changing at all the covariance. We're keeping those as the original data set was. But these more complex forms of normalization where you're like whitening the data, you don't usually see them done. So that's just like an aside. In other forms of machine learning, though, you will see them done. So like in PCA, like principal component analysis, you'll often do a lot more data preprocessing, or kernel methods, that's like another form. Okay, so why, like conceptually, why might we want to preprocess our data in the input space, like in the original image space? So this figure here is trying to illustrate conceptually why this might be useful. So if we imagine that we have some classifier which is operating on data that has not been normalized, so here on the left-hand side, let's imagine that the training examples we have to train our classifier are very, very far away from the origin. And let's say that we randomly initialize our classifier with maybe like a zero weight matrix and some, zero bias vector and then a random weight matrix. What that's going to result in is just a random classifier, like just a random line in this 2D space. If we now imagine that we were going to, during training, try and change this classifier by a small amount, because our training examples are very far away from the origin in this case, it actually will be the case that if we slightly change our classifier, we'll have maybe a very substantial change in the actual classification decisions within the data space. So imagine, like these figures are just kind of conceptual, but if you imagine sort of rotating this linear classifier by some fixed angle theta, you're going to kind of carve up the portion of space which maybe should be classified as red points very drastically. So it might make training very difficult in this non-optimized case, or in this non-normalized case, just by a mere fact that small changes in your weight matrix can have like very drastic changes in the portion of the space where your training data lies for classification. In contrast, if we normalize the data, the thinking goes that now rotating this classifier by this theta, like making some change to the classifier, will have a smaller change in the portion of the data space where our decision boundaries really matter, because we've moved our data and correspondingly where we want our decision boundaries to be closer to the origin. So they're kind of closer to where our network is centered, or where our classifier is centered. This is just kind of conceptual, though. This is a very small, like, to It's just a concept of how normalization might be beneficial. In practice, what we'll do for image tasks is normalize, as I was saying, by the color channels. So AlexNet, what they would do is actually create a mean image of the overall data set and then normalize using the mean image. So subtract, like zero center the data on the mean image. That's not used anymore though. Now what's used typically is you'll take a mean across each color channel. So you'll get 3 numbers for the red, green, and blue color channels. And you'll subtract, for every input image to your network, you'll subtract these mean values. In addition, that was sort of like VGGNet used that approach. In addition though, now what's also used is, so you'll subtract the mean values and you'll produce a channel-wise standard deviation. So you measure like what's the standard deviation across my training set red pixels, and what's the standard deviation across my training sets green pixels and the blue pixels. So you'll get 3 numbers, and you'll divide your input image after you've zero-centered it, also using the standard deviation on the color channels. That's typically what's done on all like image detection or object detection, image classification, image input tasks, pose estimation. Okay, before we go on to weight initialization, any questions I can answer on the data preprocessing? The main takeaway here is really just data preprocessing is important. It will affect the network's output, and for color image-based inputs, we will normalize by zero centering using the mean on the color channels, and then divide by the standard deviation of the on our color channels from the training set statistics. Yeah, yes, really important point. The question was, at test time, if we're going to use normalization, do we still have to normalize like an input image at test time using the same approach? And the answer is yes. So once you've trained a network using one of these normalization techniques, it's crucial that at test time you would apply the exact same normalization techniques. Not too dissimilar from how in batch normalization at test time, remember we use those running average training set statistics at test time. You have to do the same thing here. And the reason why is because then the networks, once you've trained them, they've been trained on that distribution of data that was coming as input. So if your distribution has been shifted, like the network now is sort of fitted to that shifted distribution. So now if you start giving it samples from some other from some other distribution which has been shifted away from its training set statistics, who knows how it's going to perform? Like in practice, that's what's called a distribution shift. And it's actually a research problem of how do we keep our models performing well on shifted distributions of input. In general, neural networks will not work on shifted distributions of input. They will fail in unpredictable ways usually too. So yes, it's crucial that we apply the same normalization techniques at test time on the input as we did during training. I think there was another question. So the question was like, we're saying here that we're taking the mean for these color channels, like, is that the mean over a batch from our training set, the whole training set? Like, where is this mean coming from? And the answer is it's over the full training set. So oftentimes you'll actually see like kind of copy and pasted when you look into like PyTorch models, you'll see these statistics. I can't remember off the top of my head what they are, but they come from ImageNet. So usually what people use are these exact same statistics from ImageNet. So there's 6 numbers, 3 for the red, green, and blue mean, and 3 for the standard deviation of the red, green, and blue color channels. But yes, they should come from your training set and the entirety of your training set. And the reasoning why you would want to use the entirety of the training set is because you want to get these statistics to be as close as you can to what you expect the model to see at test time. And so your training set is the data set that should be as close as in distribution as what you expect the model to see at test time. Okay, so the question was, do we normalize so at test time, do we normalize input images using the means that was seen during training, or do we use the means that was seen at test time? And the answer is definitely not the means seen at test time. So at test time, you might just get one image. And so that one image statistics, if you take like the mean of the pixels spatially across the red channel, is going to be in all likelihood, very biased based on what's in the contents of that one image. So instead what you use is the training data set's statistics. So, and those would be the same ones that you are using for preprocessing during training. So basically before training, what you should do is calculate the mean across the 3 color channels, calculate the standard deviation across the 3 color channels, I guess the standard deviation across the 3 color channels, and then you hard code those essentially into your preprocessing. And then anytime, whether it's training or test time, anytime there's a new input image, you normalize that input image first using those same fixed statistics. And then you pass it into the network. Yeah. Okay, so the question was, like, let's say I have a training set of 10 images, and during training I'm going to use a batch size of 5 images. So you'll have maybe 2 batches of 5 images, and there's 3 channels per image. The question then was, during training, will I take the mean across, correct me if I'm wrong, you were saying the mean across all this. Right. Okay. So yeah. So the question was, so during training, will I take the training batch statistics and use that for normalization? Generally, no. Generally, the main practice that's used is you would take all 10 images, you would calculate what's the mean across the red channel of all 10, and that's your red mean. You take the mean across all 10 images on the green channel, and that's your green mean. The mean across the blue channel on all 10 images, that's your blue mean. And then same for the standard deviation across those 10 images and 3 channels. So you have 6 numbers. And then during training, if you get a batch of the first 5 images, you're still using the statistics from all 10 to normalize them. That's usually what's done. I will point out, I mean, you could alternatively propose a method of normalization where you use training statistics and then you accumulate them similar to what batch norm does. But usually in practice, what's done is you just always use the entire training set statistics for both training and test time. Yeah, so in ImageNet, if you have, like, let's say on the order of 1 million images, you will still calculate the mean across all of them before training. And that's also why, generally speaking, people do hard code the mean and the standard deviation statistics into the models, because you don't, if you're running on your local desktop, you don't want to have to actually go through calculating the mean of ImageNet. Somebody else has done it, so you can just like take the results of their compute and use it. Yeah, great questions. Okay, so so weight initialization. So this is another really important kind of practical thing to consider when starting to actually train these architectures. So let's start with maybe the simplest approach we could to initialize our weights, and let's say we just set all the parameters in our network to have a weight equal to 0 and the bias equal to 0, right? So we're thinking like, oh, we'll just do kind of like the most conceptually simple thing. The problem with this is, if we think through it, if all the parameters are 0, then the output is always going to be 0, and it's going to be 0 for every single neuron of output that we have, right? So in our case of like 10 classification, of trying to classify for 10 classes, you'll have like 10 neurons. All 10 will always be 0 if our parameters are all 0. So in addition to that, because all of our output neurons are the same output for every single image, the gradients for all of those 10 neurons, and then correspondingly for every single preceding neuron in our network, are going to be the exact same, whatever they are. So there's never going to be any symmetry broken in our network. You're always going to update every single neuron the exact same way. So this will fail completely. So instead, then, the next sort of approach that you would probably think to try is, okay, let's just randomly initialize our parameters using some like, let's say, in this case, a Gaussian normal with a small standard deviation. So a 0 mean and a small standard deviation. And this can work okay for small networks, but there's an issue with deeper networks that comes up. So if we think about what this will look like, so let's run an experiment here where we have a 7-layer fully connected neural network where each layer has 4,096 dimensional output and input. So this is just setting up what are the dimensions of all 7 layers. Here we're going to store in this list here, this Python list, the history of our hidden states. Our input we're going to initialize just randomly to be, this is our input. Yeah, our input here is just going to be randomly initialized to be of dimension, so 16, I guess, channels of input and an output of 4096 based on our setting for this hidden state size. And then what we're doing is we're just going through each layer. We're randomly creating a weight matrix using this initialization scheme we defined. And then we're going to calculate what's the forward pass for this layer, right? So we're doing a matrix multiply between this x vector and so this x matrix, which is 16 images or 16 examples, each with dimension size of 4096, and our weight matrix for this layer. We're passing that through a hyperbolic tangent, let's say, as an activation function, and we're storing that into our histories. So if we run this code and then we measure what is the actual, what's the distribution of activations throughout this network for the 7 layers, what you'll find is that the activations tend towards 0. So after the first layer, you can see what the activations on distribution look like. But then as you move through the network, they're getting closer and closer to having a mean of 0 and a standard deviation of 0. And so the issue with that is that the corresponding gradients, as you have these deeper and deeper networks, are also going to move to be 0. Because if you remember, like if your activations are 0, then because during backprop, this linear layer has that swap multiplier effect, it's essentially the activations at one layer are going to be the gradients for your weight matrix at that layer. So if our activations are going towards 0 on distribution, our weight matrix gradients are going to go towards 0 for these deeper layers. So essentially, the deeper the network, you're going to have a less and less training signal. So that's one issue. Another then potential change you might make is like, we'll say, okay, well maybe we just picked too small of an initialization standard deviation. So in this case, let's run the same experiment, but what we'll do is we'll increase our standard deviation from I think it was 0.01, yeah, to 0.05, so 5 times as large. And otherwise, though, it's the same network. So it's like hyperbolic tangent activation, 7 layers. What do we find? Well, in this case, what we find is that our activations now are all saturated. And so in this case, what's happening is or if we ask the question now, like what's going to happen with our gradients, because we're starting out in this initial scheme with all saturated neurons, we're also going to have gradients that are all 0, but it's for a slightly different reason. In this case, it's not because our activations are moving towards 0, but because our weight initialization was so large, all the neurons were saturated, so the gradients through the hyperbolic tangent neurons are also going to be like because they're in that region of like the flat zone of the hyperbolic tangent, the gradients are going to be 0. So now it's like we've tried an initializer that's too small, and now we have an initializer that's too big. So the question then is, how do we tune this initializer so that the distribution of randomness is sort of favorable? And so there was analysis done. So in this paper, what they propose is what's called Xavier initialization, and the idea is you try and scale the distribution of randomness used to initialize your parameter vector based on the dimensionality of your input. And so if you use this form of scaling, what you'll find is that you can actually ensure that your activations for that first pass on distribution are going to be expected to be Gaussian with a controllable mean and standard deviation. And so what this does is this will ensure then that we don't run into those 2 issues in the preceding slides. So we're not going to run into our activations moving towards 0 mean and 0 standard deviation, but also we're not oversaturating our neurons initially, so we're going to ensure that there's a good gradient flow during training. This idea of Xavier initialization extends to convolutional layers, not just fully connected, just that the dimension that you're using in this term here is based on the kernel size as well. And I'm kind of going through this just based on time. So the thinking behind this form of initialization is outside the scope of what we want to really talk about in this lecture, but the core idea is they're trying to standardize what the variance of input and output is. So if you assume that you want the variance of your input for a layer to match the variance of the output, you can use that to then derive what the distribution of the weights should be to achieve it. And so the solution is worked through in that paper if you're interested. But there's this interesting case that happens with ReLU using Xavier initialization. And it turns out that because Xavier initialization as it was initially proposed assumed zero-centered activation function, which was the case for hyperbolic tangent, if we substitute into this experiment a ReLU activation instead of a hyperbolic tangent, we'll actually find that we have the same issue we saw in the first experiment, where our activations as we get deeper into the network are gradually moving towards zero mean and zero standard deviation. So they're all collapsing to zero, and correspondingly our gradients are going to be zero. So how do we fix this? Well, there was another paper proposed with a method called chiming initialization, named after the first author, that proposes an initialization scheme that fixes this weight initialization for ReLU. And so most commonly what you'll see used in practice is ReLU activation with chiming initialization for your weights. And let's see, there's like a slight variation of this for residual networks, and this is still a very active area of research. So how it is to actually do proper initialization is still an open question. I'll point out, for those interested in this topic, you should read this, like the lottery ticket hypothesis paper. It's a super interesting result about how a lot of the weights within our neural networks are often useless for achieving a set amount of accuracy. So it's a really interesting result. Because we're out of time, I'll stop there.